Is this the size of the Earth if you squished it down to the density of a black hole?
That's right. If that was a black hole, its mass would be the same as the Earth.
The entire Earth?
In the entire Earth.
You are honestly the exact right amount of weird.
I don't really see what's so weird about that.
This episode is brought to you by Cancer Research UK.
Imagine this. Inside all of us, billions of cells follow millions of instructions written in microscopic code. And when a new cell grows, it copies those instructions, but the smallest error can lead cancer to develop.
Right, and this is the reason why there isn't a single cure for cancer, because, there are more than 200 different types. Each of them have got different distinct characteristics, different challenges, different mysteries. And that means that trying to cure cancer isn't like following a single path. It's like trying to map out an entire forest.
That's right. And Cancer Research UK is the world's largest charitable funder of cancer research. Their work spans more than 20 countries, with over 4,000 scientists, doctors, and nurses pushing knowledge forward to save and improve lives worldwide.
Over the last 50 years, the work that this charity has done has helped to double cancer survival in the UK. And you have to think about that is more parents at the dinner table, right? That is more friends at their birthday parties. That is more people who are living longer, better lives.
For more information about Cancer Research UK, their research, breakthroughs, and how you can support them, visit cancerresearchuk.org/rest is science. Hello, and welcome to The Rest is Science. I'm Michael Stevens.
And I'm Hannah Fry.
And today I'm asking you, Hannah, when was the last time you fell over?
I fall over quite a lot, I've got to be honest with you. I think my limbs are longer than my brain expects them to be, so I get myself in all kinds of trouble. I think probably the most notable time was I was walking home quite late at night and there was a big queue for a nightclub. And at that moment, a really interesting car drove past. I was so busy looking at the car that I walked into a lamppost and then fell over backwards. And everyone in the queue saw me do it. That was not a good day.
You're a lucky duck. Because that means you got to experience weightlessness.
What, on the way down? Is that how you should think about it every time you fall over?
That's how you should think about it.
You lucky duck.
That's how you should think about gravity, which is what I want to talk about. Gravity is one of those things that we all experience constantly, can't get away from it, and yet, what the heck is it?
What the heck is it indeed? And we've got some answers, but not all the answers, as you will discover.
Yeah, so we're going to talk about the nature of that mystery, and I want to start with a challenge that I gave you a bit earlier, which I've been working on too, which is how would you describe gravity to an alien from another universe that had never experienced gravity?
Mm-hmm. Okay, let me ask some questions about this alien. Does the alien have a physical body?
Yes. And I think, by the way, these questions are very important. They kind of tease out what gravity is. What do you even need to know to experience and understand it?
Yeah.
So let's say that the alien has a physical body. It has a concept of time very similar to ours. It lives in a world where seconds are pretty fast and years are pretty long. It understands motion, okay? It understands position and acceleration.
Does it have 3 dimensions?
Yes, it lives in 3 spatial dimensions. It also lives in 1 temporal dimension. But for some reason, its universe has no gravity.
Okay.
And so it needs you to explain what it is.
Okay, well then I think that the simplest way to think of it is that in our universe, objects are attracted to each other. And if you, without any interfering from outside, if you just have 2 objects near each other, they will come together. That's it. That's it really.
And at this point, the alien goes, "What? That is so odd."
Right.
And what do you mean by an object?
Anything with mass. Anything with mass. Because I think that we sort of imagine gravity as though it's like the Earth is pulling us down. But the thing is that we're also pulling the Earth up, right? And if you get much smaller objects than planets and you put them in space, they're pulling each other and will come together.
That's right. Yeah, I once calculated that 2 baseballs placed in intergalactic space, a meter apart, would very slowly collapse in towards each other until they touched. It would take 3 days for that to happen, but it would be because of their gravitational attraction to each other. We are gravitationally attracted to each other right now. It cannot overcome the air it would have to push out of the way, the friction between our butts and the seats, but yet we are attracted. In fact, when you're born, right, you've got some zodiac constellation that's like, I don't know, it's how does astrology work?
something Pisces.
Right. Okay, so you're a Pisces if you're born in a particular time of the year. But yet the gravitational influence of Pisces on you is less than the gravitational influence of the doctor who delivered you on you.
Because otherwise, birth ain't working.
That's why, yeah, people are like, oh, so you're an Aquarius. And I'm like, no, I'm a Schnitt cookie. Because Dr. Schnitt cookie was there influencing me
to catch
at
you.
A physical level. Yeah. Not just the catching, not just the physical touch, but the gravitational attraction to his mass.
Right.
It's been with me my whole life.
Where is he now? Eh?
Now, I want to be this alien again, and I want to say, all right, so objects with mass enjoy each other's company. They come together.
They do.
What's mass?
Oh, no, now we're getting into trouble because, I mean, this very quickly gets into nasty quantum physics territories.
It does. And so let me just posit some possible answers.
Go on.
One is that, look, when I say mass in this context, I just mean the amount of matter something is made of.
Yeah.
Which in our universe does a couple of things. It affects how attractive and attracting it is to other objects, but it also affects how hard it is to change the motion of the object. And these might be different things. Gravitational mass and what we call inertial mass.
Yeah.
An object that's really hard to speed up and push around has a lot of inertia.
Like resistance to motion, you know?
Resistance to motion change.
Yes, absolutely.
And gravitational attraction, they're both related to mass. They correlate with it. But is there still debate around whether they're the same thing?
One thing I would say that those ideas of inertial mass, that objects resist changes in motion, I like to think that's sort of how I live my life, you know? Like when you're in bed in the morning, it's like I'm happy staying in bed. And then I don't like changing. So don't like getting up. Once I'm working, right, I don't like stopping working. Once I'm awake, I don't like going to bed. It's like I don't like the change.
That's right. And to change what you're doing, something kind of forceful is required. That's the vocabulary that physics uses. If something's motion changes, a force has acted on it.
Look, Newton was just a lazy guy.
So I want to take a step back and say we've been talking a lot about very like fundamental things in this really abstract way to just explain that things fall down. Because here on Earth, they're attracted to the Earth. And you were talking about how it's not just the Earth pulling things in. Things pull the Earth as well, but the Earth is so much bigger than everything else we work with. That equal attraction they have affects other stuff, like a pen, a lot more than it does the Earth. But I once calculated that if you dropped a pen from 6 feet up, it actually pulls the Earth up towards it 9 trillionths the width of a proton.
Oh, which is, by my calculation, small.
It's very small. So the pen falls the remainder of that distance, which is still pretty much 6 feet.
But they are coming to meet each other.
But they're coming to meet each other somewhere in between.
Yeah.
It just happens to be a much longer trip for the pen. And there you've got both of those senses of mass happening together, the gravitational attraction, but then also that force moves each object with very different accelerations.
I mean, that pen, though, is particularly light. If you take an object that is heavier, denser, I mean, heavier, actually, there's sort of an implication of gravity in that statement itself, right? But if you take something that has more matter, the amount that the Earth would move would change too.
That's right. That's right. And so when people say a feather and a hammer dropped in a vacuum, so there's no air to move out of the way, they will fall at the same rate. They'll hit the ground at the same time.
I tell you what, why don't we just clear up the question of what is gravity according to what different people thought at different times.
Yeah.
Because everything you're describing so far is essentially like a Newtonian view of gravity. So Newton has this idea that actually gravity is all about objects accelerating towards each other, right? You know, force is mass times acceleration was one of his laws, and he was saying that we are accelerating towards the Earth. which is the reason why when you chuck an apple or any object, your baseball if you like, when you chuck it, it accelerates towards the earth and follows this curved path. And everyone for, many hundreds of years was like, that guy Newton, he's got it made. He's done it for us. That's perfect. But there were still some lingering questions, some little things that didn't quite make sense. So, for instance, how is this force sort of acting? Like, let's say you took the sun and you had like a magic wand that made the sun disappear instantaneously. It would take 8-9 minutes for the light to hit us. But according to Newton's version of gravity, we would immediately stop accelerating towards the sun, which means that the Earth should immediately spin off into the blackness of space. But that sort of doesn't really make any sense, right? Because isn't it that nothing can travel faster than the speed of light? So how can it be that we would feel the loss of the gravitational pull of the sun before the light switched out?
Right. Yeah. And so we know for a fact today that gravity travels how fast?
Speed of light.
Speed of light, no faster.
Well, because it's the universal speed limit.
Yeah, certainly it's not instantaneous.
Absolutely, which means that if the sun suddenly vanished, we wouldn't know about it at all.
But was that a problem for Newton?
Newton, no. But as the time went on, people were like, there's something a bit fishy going on. There's something a bit weird. I'm not sure I like this. The other one that was a bit weird that people just couldn't quite work out is Mercury's orbit. The thing about Mercury, closest planet to the sun, it has this elliptical orbit. But that elliptical orbit is itself spinning around. It's affected by the other planets. So it doesn't trace out the same ellipse every single time it orbits the sun. That ellipse is moving around. It's called the perihelion of Mercury's orbit, which sort of makes sense, right? Helion meaning sun. And everyone was cool with that. Everyone was absolutely fine with that, that they knew that, the orbit was going to change because of where different planets were. But when they ran the calculations, according to Newton's version of gravity, that it's essentially just objects accelerating towards each other, something was off, right? It was like the number of arc seconds of Mercury's orbit just didn't totally make sense. And for a long time, the telescopes weren't that accurate. People were like, maybe we've just made a miscalculation. It's sort of a bit, I don't know.
And this was for a long time.
Hundreds of years. And then when Einstein came along and he was like, I think there's something else going on here. Einstein has this great intuition that it's not just that objects are magically accelerating towards each other, but that space-time itself has this curvature to it. So the sun, for instance, this giant gravitational force is literally bending and warping space-time between us and it. And so if you got a magical wand and you made the sun disappear immediately, there would be this ripple that was sent out from the absence of that sun. Like imagine taking a bowling ball on a rubber sheet and then removing it. That rubber sheet is going to kind of bounce up and down and ripple as you remove the weight. And that ripple would reach us at the speed of light. He had this great intuition, worked out all the calculations for it. And one of the very first things that he turned his equations to was the perihelion of Mercury's orbit, to see if his new theory came up with a more accurate prediction than Newton's. And he absolutely nailed it.
Nailed it.
Level of precision. I mean, he said that he was happy for days after he looked at those calculations, was like, I've absolutely got it. I found the missing piece to the puzzle.
So 2 things. First, that leap from there's a force acting on things, maybe it's mediated by some particle or whatever, to leap from there to actually maybe gravity is just a change in the shape of space-time is really gigantic. Because space-time is such a bizarrely abstract thing. It's the canvas that we are on. If we were 2-dimensional, this would be easier. We could say, a 2-dimensional creature could be painted onto this curtain. And if I crumple the curtain up, they're still stuck on it and they're going over all of these crinkles, but they don't even know it. I can bring them together and push them apart. If it gets crumpled up or curved, you're just going to follow along that curve. You cannot leave it. And so, Einstein is like, but what if it's the shape of the canvas that we are on?
Exactly.
Even the shape of time and how quickly time runs for you. If we allow that to change, then Mercury's orbit makes sense.
Exactly right. They're crumpling the curtain. That's a really nice way to do it.
Yeah, I think you need analogies because we're just talking about things that are so outside of our normal day-to-day activities.
Totally.
We understand forces. We understand pushes and pulls. But to say that space and time themselves push and pull, it's kind of more like you're just in them.
But here's the thing, right? The implications of this idea that space-time is like a crumpled curtain, it means that across the surface of the Earth even, the gravitational effects are slightly different. So I did some calculations. Boulder in Colorado, right? Which of course is like a very high altitude compared to Greenwich in London, where I am. The gravitational effect in Boulder is 9.796 meters per second.
And what is it in Greenwich?
9.812.
Wow.
I've got higher gravitational effect than you.
Yeah. So you are more attracted to the center of Earth than I am in Boulder.
Yep.
Because I'm further away.
Yep.
And the inverse square law says
exactly.
that
Further away,
gravitational
drops
effect
away.
Diminishes.
Except that what that means, given Einstein's version of gravity, is that the way that time changes in Boulder is different to the way that time changes in Greenwich, because what gravity is doing is it's bending and warping space-time. So what this means is that time travels slower in Greenwich than it does in Boulder. And the difference is about 5.6 microseconds a year. So what I will say is that you are aging faster than me.
I am, but relative to who? Because my proper time is going to feel very normal to me.
Sure.
Meaning the time that I'm looking at, I'm looking at my watch, it all feels normal. But if I could somehow look at your watch, I would notice that it was running behind. That's because you're closer to Earth's center of mass. Gravity is stronger where you are, so time runs more slowly.
I mean, this stuff is so
It's mind-blowing, it's mind-warping, it's space-time warping, but it's also experimentally confirmed.
Absolutely.
And that's, I think, something that we should pay more attention to when talking about, because it makes it seem more real. Like, they've done these experiments. They've taken really accurate clocks and put them up at high altitudes and down at low altitudes and seen that this exactly happens, that time runs more slowly on the lower clock.
But we should also be said, we're not talking about like stopwatches here, right? We're talking about like atomic clocks, which are, like based on the most precise measurements that it's possible for humans to take with the technology that we have at the moment. And the calculations, they're not just like close, they are like dead on the nose.
If Einstein had had these ideas in the 1200s, confirmation would have eluded them for a long time.
I mean, the idea of 5.6 microseconds a year is like, you just don't really notice it, do you?
You wouldn't notice it.
No.
Yeah, he would have been seen as just a guy writing some cool fairy tales.
Yeah. One thing that I do think is interesting, though, is that, as you said, right, this is the canvas that we're living on. It's not something that we're noticing. And actually, they've done these different experiments where they've taken earthbound creatures, right, and taken them up into space. Not just humans, but to see how they behave and how they react. And fish in particular, there's something interesting that happens. If you take earth-born fish up into microgravity in space, the ISS or whatever, they're completely disoriented. They sort of don't know which way is up. They're like really struggling to swim. They're just, they don't have a good time. But they can have babies in space, right? And they have managed to breed them. When the babies are born, right, these kind of little fish eggs hatch, those babies, absolutely fine, totally chill about it.
Interesting.
Swim back normally.
Do fish come into the world as a blank slate, ready to learn it? And if they learn gravity, then they can't forget it?
Well, I think that's the hypothesis, right?
Yeah.
But they also did this with octopuses, octopi. And the octopuses that were born in space seemed like they were fine. And then when they came back down, they really struggled. They struggled on Earth. Yeah.
I feel bad for those.
I know.
And now here's like where you're supposed to be living and there's gravity and it just feels like an oppressive force squishing you all the time.
Exactly.
You're welcome.
It would be so much worse that way around, wouldn't it, right? If you go, I think I would rather be born in high gravity and move to low gravity than the other way around.
These poor like water animals that we're subjecting this to, it's harder for them. For us, we need that gravitational force for our bones to develop properly. A human baby born in space in the so-called zero-G weightless environment, their bones would not grow properly. They would look like they had rickets. I did a video about this, and it's very gruesome what would happen if you tried to grow a human in with no gravitational tension on their bones. I think we tried this with rats as well, birthing rats in space. And yeah, they didn't do too well in space. They really need that landlubber gravity
in order to form properly.
Yeah.
Yeah, I mean, some science experiments aren't that nice, are they?
No, they were all okay, by the way. This was just like a minor inconvenience, and now they've got a good story to tell their friends. Is how I choose to look at it.
It was worth it for the anecdote that they got.
That's right.
Yeah. These visualizations of warping of space-time, though, I mean, should we talk about those a little bit? Because I think there's some that are quite common. You see them around a lot, right? Like I sort of even use for myself there, the stretched rubber sheet with Earth as a bowling ball sitting in the middle of it. I mean, they're kind of useful in a way, but they're also quite limited because we ourselves are not capable of comprehending these extra dimensions.
Yeah. I've never really liked the rubber sheet analogy because it doesn't seem to do anything but just show what you already feel, which is that gravity makes things fall. They rely on gravity to demonstrate gravity. And also they're shrunk down to just the two-dimensional plane of a sheet of rubber. We're talking, of course, of the demonstration where you've got a rubber sheet, you put something really heavy in the middle, and it sags. And then when you put like a little marble on it, it rolls down towards the big, heavy, massive object. And you say it's because of gravity. I mean, of course it's because of gravity. That's why everything rolls downhill.
Well, you try and get a gravity-free situation on Earth in which to demonstrate.
Yeah, and then also you can take a marble and you can throw it out tangentially towards the slope, and it'll orbit the heavy object, go around and around. But it loses energy so quickly, it always spirals into the thing. And I just feel like, especially for students, they go, well, but Earth isn't doing that. We aren't spiraling into the sun. So clearly I'm not learning anything about Earth and the sun.
Yeah, it's where the analogies break down.
Yeah.
The one that I do like, and I think this was Richard Feynman, he was saying the reason why it's difficult for us to imagine additional dimensions, if you take a piece of paper and you imagine that you have an ant living on this piece of paper, and the ant is so small that it's effectively two-dimensional, right? It cannot conceive of up and down, because even when it climbs up a wall, the curve between, or the corner between, the ground and the wall it's so tiny that it's like, it feels like it's just this continuous surface.
Yeah.
But if you take an ant on a piece of paper and you say, this is point A, this is point B, and you ask the ant, what's the quickest way between these 2 points? The ant's going to say, it's a straight line between the two, right? Which is like, yeah, great, well done, ant. But you could take that piece of paper, and because we have an additional dimension, we have 3 dimensions, whereas the ant only has 2, you can fold the piece of paper and make A and B combine in the same point, right? You can effectively create a wormhole that the ant didn't see coming. And this is sort of a way to explain why this stuff is so difficult for us to comprehend, because once you bend that canvas, once you warp that curtain, I mean, everything sort of changes. The rules slightly go out the window.
Yeah, and that analogy is great, but you can also see how hard it is to jump up to where we live.
Yeah.
Because I can imagine a curtain folding and things that live on the curtain not understanding. But how do I bend 3-dimensional space, not a flat curtain, but like a whole universe? Where am I bending it into? Some other dimension.
Yeah.
A fourth spatial dimension.
A fourth spatial dimension.
Have you ever tried to visualize a fourth spatial dimension, a fourth line that could be perpendicular to 3 others?
I mean, you can't, right? You can only imagine slices of it. You can only imagine 3-dimensional slices.
You don't think it's possible?
I mean, you can describe it mathematically. That's like very easy. I mean, for instance, you could take like a square, right? Or a cube. I could tell you the corners of a cube are, there's one at 0, 0, 0, there's one at 1, 1, 1, there's one at 1, 0, 0, and so on and so on. And then if I use the language of mathematics, then it's really easy, right? Because I can just say, 4-dimensional one, it has a corner at 0, 0, 0, 0.
Yeah, you got 4 coordinates. Fantastic. I'm still not feeling it.
You're never going to feel
it.
You're never going to see it.
Why do you think I can't?
I just don't think that your brain is capable. And that's not just you,
This is,
Michael.
how a lot of people count sheep when they go to bed. Yeah. I try to imagine a way to look inside a hollow sphere by looking from a fourth spatial dimension. And I haven't succeeded yet.
You surprise me. All right, well, I hope we've suitably warped your minds. Should we go to a break?
Yeah, let's do it. All right, welcome back. from the break, we've talked about Newton and Einstein's theories. Where are we now?
Okay, so here's the thing, is that everyone was like, Einstein's such a genius. Everything's stitched up. It's all great. No, there's still so much more. There's still all of these big questions that it's like, why? It doesn't quite work. It doesn't quite work. So one of them, there was a cosmologist called Fritz Zwicky, one of my favorite cosmologists of all time.
It's a good name.
It's a great name. And also he was a proper curmudgeonly old git. He wasn't a very nice guy, right? And he had a saying where he would say of his colleagues that they were spherical bastards because they were bastards from whichever angle you looked at them.
Ah, very clever.
I mean, he is a super smart guy.
Yeah.
Anyway, he was studying this galaxy, the Coma cluster, and he was like, well, you know what? Something's going on with gravity here. Something's not quite right. Because these galaxies are spinning around so fast that if the only gravity that's present is the gravity that's coming from the stuff you can see, then these galaxies should be spewing stuff out, right? They should be ripped apart by the speed that they're spinning. And so him and a number of other cosmologists were like, okay, something is not adding up in these equations. There's something that's not right here. And so rather than kind of going back and undoing Einstein's versions of gravity or undoing Newton's, they were like, well, they look like they're right. So maybe what's going on instead is that there's all of this other stuff that we just can't see.
We can't see.
So it's like matter that's like not reflecting light. Maybe we should let's just call it dark matter, add an extra term in our equations, everything's good, everyone can go home.
And that's the birth of dark matter.
That's the birth of dark matter, and frankly, how dark matter has long remained.
Wow. I didn't know that Zwicky was also part of the dark matter invention/discovery. Yeah. We know a lot more about dark matter today.
We do. We don't. Still haven't found it.
What does it mean to find it? Like, what would it... I was going to ask what it looks like. It doesn't look like anything. It doesn't interact with light. But could you have a jar full of it?
Yeah, I mean, I'll be honest with you. Every jar you've ever had has probably got some dark matter in it.
But there must be a small amount because there aren't a bunch of gravitational anomalies caused by this invisible matter in our day-to-day lives.
Yeah, but it's here.
So dark matter, though, the actual substance that's in the universe and around us is still very mysterious.
Still very mysterious. And there's other things that are mysterious here too, right? There are other things that gravity doesn't totally explain. I mean, Newton, in a way, sort of wrapped up what gravity is doing at the scale of humans, right? That's sort of the scale of us wandering around.
And how to write formulas about it and predict what its effects will be.
And you get really accurate predictions at the scale of kind of humans. Einstein then did it for the scale of galaxies, the scale of solar systems, amazingly accurate predictions for that. But what we still don't really understand is how gravity works down at the level of particles, because there's some weird stuff about it, right?
Right.
You have all of these forces. You've got the electromagnetic force, you've got the strong nuclear force, which is the thing that sticks atomic nuclei together. You've got the weak nuclear force, which is what's responsible for radioactive decay. But each of those have a particle that does the job.
Ah, right.
So the electromagnetic force, for instance, it's the photon that does the job. Like the photon physically travels between the emitter and the receiver. And that's what's doing the work of that force.
Okay, which one is gluon?
Gluon is the strong nuclear force, and then the boson is the weak nuclear force.
Okay, so gravity?
There isn't one, or at least we haven't found one.
But is gravity a force in the same way?
Well, who knows? So we don't know for sure, right? It might be that, yes, gravity has a graviton, which is the sort of supposed name for this particle that's doing the job. And if that's right, then the theory is that gravity sort of flows between things mediated by these particles in the same way that sort of, water flows because of lots of H2O molecules that are moving. That might be the case, or it might be that gravity is actually this emergent property like temperature or pressure, and it's not this fundamental force of the universe, as the weak nuclear force, strong nuclear force, and electromagnetic forces are. And we don't know. We don't know the answer, right? But if there is a graviton, and believe me, we've been looking for one.
Yeah.
A lot. They're really, really, really hard to find.
How do you try to find one?
I mean, you would need a particle accelerator that was basically on the scale of a galaxy.
Let's get started.
I would say hard. Because the thing is that if you compare, you take a magnet and a pin, right? And you can overcome the gravitational force.
Gravity is very weak.
Incredibly weak, right? Like 10 to the minus 38 times weaker than the other nuclear forces.
Right. Like protons and neutrons are never like, whoa, make sure you don't fall out of the nucleus because of gravity.
No, they don't care.
Right.
They don't care. They don't ignore that guy.
Super weak.
Super weak.
Oh, right. So this is where these theories of, well, maybe gravity is just as strong, but it's like it leaks.
Yes.
And that's why it's so weak for us.
Well, maybe gravity exists, inverted commas, in different dimensions.
Right.
Maybe we're not in a four-dimensional if you include time. Maybe we're not in this sort of three-dimensional space at all. Maybe we're in a space with 5 dimensions, 11 dimensions, 27 dimensions. Maybe these extra dimensions are like us and the ants, right? Maybe they're so vast, so big that we cannot possibly conceive of where they are. Or maybe we're the giants. Maybe these extra dimensions are curled up really tightly in little, this is the idea of string theory, basically. We've got all of these additional dimensions that we just can't experience because we're just way too big to.
We're too big. Yeah. It's like, you had this analogy of an ant on a tube. And if the ant's big enough, it's basically just on a one-dimensional surface.
Absolutely.
But smaller things would say, no, you can go around.
Yeah.
I can be underneath you. And he's like, what does that mean? Well, let me ask you this. Do we know properties of gravity like, electromagnetism can be like blocked, right? It can be absorbed. Things can be opaque to light.
Yeah.
Can things be opaque to gravity?
Doesn't look like it.
Okay.
Doesn't look like it. It's not like you can say, here's a gravity shield.
Right.
And just suddenly you don't feel the effect of the Earth.
And I guess then there's also not like a gravity reflector.
No, there's no gravity mirror that we know of, but there is an electromagnetic mirror.
Yeah, sure.
To be fair, there isn't a shield for the weak or strong nuclear forces either.
Oh, okay.
You can't be like, stay out, proton.
Right. Or right back at you, neutron. Yeah, okay. Here's the thing. When you've got stuff like dark matter and gravitons that we just don't know the nature of very much, they become wonderful seeds for wild speculation. Mm-hmm. Right. So if gravity is leaking into other dimensions that are just so small that we don't notice it, then, maybe if we got close enough to an enormous concentration of matter, we would notice that like gravity was much stronger there. But because it's leaking into these like micron scaled dimensions, that by the time it reaches our scale and the scale of planets, it's just doing this inverse square thing.
This tiny weak
thing.
And
I know that we've tried this. We've tried to measure gravitational attraction between objects whose center of masses are just microns apart. And we haven't noticed a change in the equations of gravity. The problem is to get smaller, we've got to be able to concentrate mass in a smaller and smaller place.
We need to get denser and denser and denser.
We need to get denser and denser.
Because otherwise gravity's just not doing anything.
Yeah. I brought a bunch of dense things here, right? First of all, here, we'll just start with the densest one. Why work our way up? That is a pure cube of tungsten.
Amazing.
And it's 2 inches. Cube.
You feel like something's going on.
Yeah.
I mean, you feel like you're getting in the way of a magnetic pull.
It's a bit like a spiritual crystal for me. I can just hold it and meditate on gravitational attraction. Like that wants to be with the earth.
It wants to be with the earth.
And the earth wants to be next to it. It feels like a magnetic kind of attraction.
It really
does. It's not just, this is a lot of effort to lift, but it's like, where are you going? It's very, very cool. And I've got an inch cube of tungsten, which is not nearly as heavy.
Well, it's a ninth of the weight.
But if you compare it to this cube, which is the same volume and yet made of steel, you really appreciate how much more dense tungsten is.
Oh, yeah. Oh my gosh, I was actually struggling to hold it out from my hand, 2 of them together.
I know. And strange things happen when you get an enormous amount of mass concentrated in one place. The gravitational force, the curvature of spacetime, reaches an extent to which even the fastest thing in the universe can't escape.
Namely light.
And if you don't have any light, you're dark, you're black holes, right?
Absolutely.
So another thing I brought along is this sphere of tungsten. And this sphere is 8.87 millimeters across. Do you know what's special about that number?
Tell me. You want me to guess it?
Yeah.
Okay, wait, tell me how far across is it?
8.87 millimeters.
8.87 millimeters. Okay, so what we're thinking is something extremely dense.
Yeah, we're talking about black holes.
Black holes. So if this was a black hole,
Yeah.
is this the size of the Earth if you squished it down to the density of a black hole?
That's right. If that was a black hole, its mass would be the same as the Earth.
The entire Earth?
In the entire Earth.
Everything you've ever known or experienced.
Everything that's here, you don't throw any of it away, you just squish it down to that size. Then you'd be close enough to enough mass, you could never escape that. That is Earth's Schwarzschild radius.
If you did manage to create a black hole this size, let's maybe not use the matter of the Earth to
No.
create
Leave us alone.
I'd sort of, prefer that everyone I've ever loved remained intact rather than compressed down into sort of infinite density. But let's say that you could manufacture a black hole this size, then experimentally it'd be way easier to find gravitons.
Yes, it would.
And then we might actually have an answer.
And that's why I think someone should do it. I don't think a black hole that size would be very dangerous. I think it would evaporate away pretty quickly, and it would just fall right to the center of the Earth. Like, would there be no way to contain it in a laboratory?
But hold on, wouldn't a lot of stuff swirl inside it on the way down?
Very little stuff would swirl inside because the stuff wouldn't all fit. It would crash into itself. Mm-hmm. And so what you would wind up with is this immense energy, high density ball of plasma surrounding it. And so it would be explosive, but it wouldn't eat up all the matter really quickly. All that matter would have to work past itself to finally get in to make room for new. So it wouldn't suck everything in.
No big deal, you say.
No big deal.
You are playing fast and loose with the future of our planet.
Let me show you something else though. This is an EDC card that we made, an everyday carry card. I'm sure people have seen things like this. If you're just listening, this is a credit card sized piece of steel. It looks just like the kinds that they sell that have little rulers on them and a bottle opener. So it's like a useful thing. But we wanted to make not a multi-tool, but a multi-fool. This is the most useless piece of steel you could ever carry with you. It wasn't even cut at right angles.
Amazing.
This is 88 degrees, 92, 87, and 93.
Amazing.
There's a lot of silly things on here, but that hole is also 8.87 millimeters in radius. Which is to say that so if you're ever really feeling down, you can just put this on the ground, and if Earth doesn't fit through there, at least Earth hasn't become a black hole. You're welcome.
Thank you, I hate it.
It also has written on it how to say hello in 10 languages no one speaks anymore.
You are honestly the exact right amount of weird.
I don't really see what's so weird about that.
I guess on that note, we'll finish for this show. So please do like and subscribe. Send in your comments to the rest is science at gohanger.com.
See you next time.